This is Unit 7, Video 2. In this video, we will be taking a look at some other physical properties of liquids. We've talked about boiling point in the previous video. Here we'll talk about something called surface tension. Now this is a very interesting, very fun physical property, and it relates to the force, the strength of the force on the surface of a liquid. So it turns out that on any liquid, doesn't matter, the surface molecules on the liquid have a stronger attraction for each other than the interior molecules. And you can say, usually it's explained this way, that the interior molecules have more partners to bond with versus the surface molecules. The surface molecules, there's nothing above for you to bond with, so you can actually form stronger bonds with your buddies to the left and to the right and below. So you have stronger attractions on the surface. And here it says, here we have some pictures to represent this. So first of all, here's a little water strider. Hopefully these are coming out in the springtime soon, and they're able to walk on the water or just kind of rest on the water. And you can see that the water there's almost like a film on the surface of the water, and this film is the surface tension. This happens in every single liquid. It turns out to be extremely strong in water, again because water is so special. You can also do the same thing. You can float a little paper clip. If you're careful, you can actually float a little paper clip on water, and it'll float because even though the paper clip is made of steel, which is 7-8 times more dense than water, because of the surface tension that can actually hold. If you take a look at this picture here, this is just a picture of a water droplet, and what many people don't realize is that water droplets are spherical. So anytime you suspend water in air, especially if it's a small enough water sphere, it'll be spherical. A water droplet, sorry, it'll be spherical. And they've done this in the absence of gravity, and big bubbles of water are actually spherical. And so when you see a tear being drawn, that's the incorrect picture. You want to draw it spherical. And that's because, the reason for this, is because the surface tension pulls the surface molecules closer to each other, closer to each other, closer to each other, creating a sphere. That's why it always becomes spherical. There's some neat videos of them playing with water on the ISS, the International Space Station, where gravity is not an issue, and you have huge globs of water forming spherical shapes. Now, if you take a look at the temperature and how it affects surface tension, almost in all cases, as you increase the temperature, the bonds begin to weaken. You'll see that these intermolecular forces weaken, and this effect starts to decrease. So here, as you increase the temperature, the surface tension actually decreases in strength. Here we're going from the freezing to the boiling point of water, so quite a bit of a decrease, or a noticeable decrease. Viscosity is another interesting property of liquids, and it's defined as the resistance of a liquid to flow. And oftentimes whenever you buy some oil, engine oil, they'll actually put the viscosity on there. This number here, 5W30 or 10W20, refers to the viscosity, how thick the liquid is. And this increases with stronger intermolecular forces. So the stronger the forces, the thicker the liquid, the more resistance there is to flow. So it starts, behaving less like a liquid, you can say even, and becomes thicker, more like a solid. And two pictures here. Here you have two types of oils. You can see that this one's thinner, and this one is, rather you can see that this one is thicker. So this one would be thicker, and this one would be thinner. So the thicker one has a higher viscosity. Viscosity is high here, and you can actually see the way it bends. Now this bending, not bending, but this surface globule that you get is actually from surface tension. So the stronger the surface tension, the slower it pours out. So this is supposed to be pouring out slower because it has a higher viscosity. This is supposed to be pouring out faster, that's why it's higher, and you can see it doesn't bend as much. You don't have that form. And here are the different viscosities of different substances. What you'll notice is that water has a pretty low viscosity compared to some other chemicals. Sulfuric acid has a very high viscosity here. So water actually it flows pretty easily, but that's because it's a small molecule. Most other molecules that are comparable to water will actually have a lower viscosity than water. And then here you have which is liquid metal. So viscosity deals with liquids, and it's the resistance of a liquid to flow. Let's talk about some phase changes, and then we'll be able to define some more physical properties. So you may have recalled these from a previous class, but whenever we melt something, then we're going from a solid to a liquid. And sometimes we call it fusion for a fancy word. So fusion or melting. And this is an endothermic process. Remember, endothermic processes absorb heat. And the reason you absorb heat when you're melting is because going from a solid to a liquid, the particles have to essentially speed up, and they have to break the bonds. Bonds must be broken to go from a solid to a liquid, and that's why that's an endothermic process. Same thing for vaporization, going from a liquid to a gas. That's an endothermic process because you actually have to completely break the intermolecular forces. Gases, remember, have no intermolecular forces. So you're completely breaking the bonds, so that's going to require a lot of energy, and more so than when you're melting something. And then sublimation, you may have heard of this. Sublimation is we skip the liquid phase, go from a solid directly to a gas, and that's also an endothermic process. So these three, if you were to put numbers on them, this one would win. This one would have the highest number because there's the biggest change from a solid to a gas for a given substance. Then we got the opposite phase changes. We got freezing from a liquid to a solid. That's an exothermic process. Exothermic process means heat is released. Remember, you can think of this as heat exiting the system. Exo, exiting, out of. It means out of. And same thing when you're condensing. You're going from a gas to a liquid. The particles have to slow down, and as they slow down, they must give off heat and give quite a bit of heat. It's quite exothermic. And then deposition is the word given going from a gas to a solid. Think of the word deposit in there. You're depositing a solid down. Another phase change that's similar, that's usually not mentioned, that I'll mention here, is liquefaction. Liquefaction is usually referring to a gas becoming a liquid at room temperature by compression, through compression. So you can actually liquefy a gas by compression, and this is not called condensation, even though it's the same thing, gas to liquid, but it's called liquefaction because condensation usually you have to decrease the temperature. Alright, hopefully this is a review, and this probably is something new. So heats of fusion and heats of vaporization. These are something called latent heat. The word latent means, it's just sitting there to be discovered or to come out. It's not coming out just yet, but it's sitting there. That's what the word latent means. The heat of fusion is the energy required to change a solid at its melting point to a liquid. So if you can measure how much heat it requires to melt something, this is the heat of fusion. You can actually measure, and this can be measured on a molar basis. It can be measured on a gram basis. Usually it's measured on a molar basis, and I'll show you this in a minute. The heat of vaporization is a similar concept. How much heat it takes to vaporize something at the boiling point. So you have to be at the boiling point, you have to be at the melting point of these two. And by the way, vaporization is similar to evaporation. The difference being that evaporation usually happens at room temperature, whereas vaporization happens at the boiling point. That's really the difference. If you ever encounter those two terms, they mean two slightly different things. So vaporization is at the boiling point. And we measure all this in kilojoules per mole. Usually it's a per mole idea. So for example, you can ask yourself, okay, how many kilojoules, how much energy must I put in to boil 1 mole of water? And that will be given to you by the heat of vaporization. You can ask, how much energy must I put in to melt 1 mole of solid ice? And that will be given to you by heat of fusion. And that's what these two are referring to. And they're called latent heat because that heat is, is hidden until you try to melt something, try to boil something. And here are the heats of vaporization, heats of fusion of different substances. So we have 4 substances to look at. Water actually has a pretty high heat of vaporization compared to other substances. So here butane, and what we see here is butane is nonpolar. So this has just Lund dispersion forces, being nonpolar. Now diethyl ether is slightly polar, so it has Lund dispersion forces and slight dipole-dipole forces. Actually, ethers usually, I really shouldn't say that, ethers have very, very weak dipole-dipole forces. And you can see that by the fact that it just increases by a little bit. Even though it has an oxygen in the middle, that oxygen is symmetrical. But water, having hydrogen bonding, actually quite strong. So its heat of vaporization is quite high. And again, this is on a per mole basis, so it's not on a per gram basis. And it turns out a mole of water weighs much less than a mole of diethyl ether, so that's actually pretty impressive. If you count out the mass of this whole molecule, it's going to be quite a bit higher than water. So water, having such a low molar mass, can still win over those two liquids because of hydrogen bonding. You can definitely see that because of hydrogen bonding. And then mercury is pretty heavy, has a molar mass about 200, so it is expected to win over water just because it's so heavy. It's kind of the idea. Now, what you see in all of these cases is that the heat of vaporization is bigger than the heat of fusion, and this is important. So this is much bigger. In water, you can definitely see the heat of vaporization is bigger. So with heat of vaporization, you're completely breaking the bonds, completely breaking the intermolecular forces, breaking IMFs. Whereas with heat of fusion, you're going from a solid to a liquid, so you can call this as loosening the intermolecular forces. They're still there, but they're not keeping the molecules together as a solid anymore. You're loosening the intermolecular forces. I meant to say loosening with the quotes around loosening. That's the idea. So heats of vaporization, heats of fusion, an important concept. We're actually going to use these in calculations soon. Let's take a look at heat capacity and something called specific heat. Now, heat capacity is the amount of heat required to raise the temperature of a substance by 1 Celsius or 1 Kelvin. So this is before you get to the boiling point. For example, what if you want to heat up water? We can ask the question, all right, if I want to heat up water by a few degrees, how much heat must I put in? And that's what this is talking about. There's something called specific heat capacity, which is then given on a gram basis. And this number we'll also be using in some calculations. Specific heat is given, we usually use a little c or a little s. If it's specific heat, it's s, but they're interchangeable. So it's the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. So famously, the specific heat of water is 4.18 joules per gram degree Celsius. What this means is if you want to raise the temperature of 1 gram of water by 1 degree Celsius, you must put in 4.18 joules of energy. And water, again, has a pretty high specific heat as compared to other substances. So here, notice water, and its specific heat is the highest of these other molecules, even though the other molecules are quite a bit heavier. So their dispersion forces are actually quite a bit higher. Notice water wins. And this property is actually really interesting with water. Essentially, it takes a lot of energy to heat water up, so water can store a lot of energy in it, and between its molecules. Between the intermolecular forces, it can store a lot of energy. That's kind of a strange idea, but it is true. And this idea is called heat capacity. We're going to essentially be referring to this as specific heat. So this is the term I'll be using when referring to this property. This will say specific heat of a substance. Another way of looking at this is to compare water against something like gold. And you can think of, again, specific heat or heat capacity as a measure of how much energy a substance can store inside of it. If you take gold, you have a kilogram of gold versus a kilogram of water. If you heat up a kilogram of gold, it'll go up by all the way up from 20 up to 9 degrees Celsius. Now, if you give the same amount of energy to water, the exact same amount of energy, it'll only go up by a little bit, by about 20 degrees. Maybe less than that. Actually, here it says it's quite a bit less. This is just the visual. This isn't referring to, so just by a few degrees, in other words. Here it says it takes 32 times longer to heat gold up, water up than gold. Water takes 32 times longer to heat it up than gold. This is because the heat capacities and the specific heats of gold and water are about 32 times different. So the specific heat of gold here is 0.129 joules per gram degree Celsius. So it takes just this much energy to heat up 1 gram of gold. And it takes this much energy to heat up 1 gram of water. So water can hold a lot more heat. That's where the 32, if you divide these two numbers, you'll get the 32. So water can hold 32 times more heat than can gold, and that's kind of the difference. All metals, as you'll see, will have a low heat capacity, and that's because metals are good conductors. This makes sense. If gold is a really good conductor, which it is, it will pass the heat right along. It will not keep it, it will not store it. But water actually can store heat quite well. Alright, and vapor pressure is related to the strength of the forces as well. Here it says Vapor pressure is the pressure exerted by the vapor of a liquid as it evaporates. So what we can do is, this term is evaporating. We're not boiling it. We're not heating it up. We're simply letting it sit there. So if you just simply fill a flask with water and let it sit there, remember we talked about this with gases, there's going to be a bunch of water molecules in the air, in the vapor. They'll become vapor. And you can actually measure this pressure. And as you measure this pressure with a closed container, this will be called the vapor pressure of water. So here it says substances with strong intermolecular forces have low vapor pressures, which makes sense. If you have strong bonds between the molecules down here, they will not become a gas. They'll remain a liquid. So they'll create a smaller pressure here up above the liquid. And so vapor pressure is actually inversely related to the strength of the intermolecular forces. So if you have very strong intermolecular forces, it will not create a high vapor pressure. And volatile liquids then will have high vapor pressures, so things that evaporate easily. Acetone is an example, alcohol is another example. They'll use alcohol in disinfecting fluids and liquids and so forth because it instantly evaporates after disinfecting. It doesn't seep in and it doesn't stay there. So it's a volatile liquid. Non-volatile liquids are more like oils. Now I put water in here. Water is technically halfway. It's kind of volatile. It's easy to vaporize water compared to oil. So non-volatile liquids will have low vapor pressures. Water will probably be somewhere in the middle. And you can actually affect water's vapor pressure by changing temperature quite a bit. Alright, let's finish up with this one, and I think there's one more slide to wrap up the second video. Predict which would have the highest viscosity and the highest vapor pressure under liquid conditions, which means we're assuming all three of these are liquids. Now here, just from your knowledge of water, oil, and gasoline, we know that oil has a pretty high boiling point compared to water. We know that gasoline vaporizes easily as compared to water. So we think that oil has the strongest bonds, and this is true. Oil does have the highest viscosity. So we'll put viscosity, so highest viscosity. And then conversely, it'll have the lowest vapor pressure. Okay, and gasoline, on the other hand, is the opposite. It has the lowest viscosity. If you ever try to pour gasoline, it just goes all over the place. It does not keep together. So lowest viscosity. And then it has the highest vapor pressure. Gasoline vaporizes quite readily. That's why they use them in cars to power cars, because you got a gas exploding down. So high vapor pressure. Okay, so then water will be in the middle. So highest vapor pressure. Water in the middle. So water actually has a decent enough vapor pressure where you have to consider it, and a low enough viscosity where you can pour it from one container to another with no problem. Okay, for B, if you take a look, we have very similar molecules, and here what you're looking at is just the dispersion forces, the strength of the dispersion forces. So because this guy has the biggest molar mass, because it has the most atoms, here you'll have the strongest dispersion forces. So this one will have the highest viscosity. Lowest vapor pressure. And then conversely, this one will have the lowest viscosity, highest vapor pressure, because it has weaker dispersion forces. So lowest viscosity, highest vapor pressure. Vapor pressure. That's the idea. So hopefully this makes sense. This probably is an easier thing to understand now. You can apply these intermolecular forces to the properties of these liquids. Alright, let's finish up with this. There is one more fun physical property called capillary action. And these are liquids getting pulled up by solids, technically because of the attraction of the liquid for the solid. So we're kind of transitioning now into talking a little bit about solids. And what happens if you have a liquid that has an attraction for the solid, and it has an attraction for the solid because the intermolecular forces are similar, what will happen is it'll crawl up the side of the solid. So in this case, the solid is glass, which is made of silicon dioxide, which could be thought of as being polar in a strange way. And water will actually create a little bending action. So if it's glass, so this bend is called meniscus. And this happens because water technically is trying to crawl up the test tube. Now, if you make it a really small test tube, you'll really see the effect. The effect's actually going to be pretty drastic, like in this case. If you make a really, really thin tube, the water will crawl up pretty high. And this is called a capillary. A thin tube is actually called, in science, called a capillary. This is just thin tube. And so that's why this is called capillary action. But it's strange because the opposite happens if you have a liquid that does not have the attraction for the solid. So in this case, we replace it with another solid that this solid has a different intermolecular force than the liquid itself. So the opposite will happen. It'll actually dip below. And you can see the capillary action will just go down to the bottom, which is strange, very strange force. If you put a paper towel in a liquid, the liquid actually crawls up the paper towel. Eventually, it'll get the whole paper towel wet. And this is actually how trees are able to pull water up through their roots and nutrients up through their roots and so forth. A tree, just like a paper towel, actually has little tiny fibers in them. These fibers you can think of as tiny capillaries in a sense. You know, they're intertwined, interconnected, and actually it makes this water keep crawling up and up and up until it gets the whole thing wet. And this is done against gravity because of capillary action. So here's a connection to the idea of liquids and solids. All right, we'll wrap this video up.